In those last examples, we saw that our functions 1 over x and 1 over x squared both tended towards infinity as x got closer and closer to 0. Not the exact same kind of infinity in every case, but it did tend to just explode up or down away from that value, always trying to get closer and closer to that location, always trying to get closer and closer to x equals 0, but never crossing or touching. And that sort of behavior is a thing called an asymptote, where asymptote comes from Greek meaning to not meet. And for these, we're essentially describing lines. They're not actual lines, they're sort of imaginary lines that can't be crossed when we're dealing with this sort of function, this sort of behavior. In particular, rational functions lend themselves really nicely, really repetitively almost, to dealing with asymptotes, where we have vertical asymptotes if they're of the form x equals a, that is, if the asymptote has the behavior of a vertical line, and horizontal asymptotes if they're of the form y equals b, that is, they take the behavior of a horizontal line that cannot be crossed. And we can picture roughly what each of these things might look like for various locations, for various types of behaviors, either in terms of those vertical asymptotes, or for that matter, in terms of horizontal asymptotes. There isn't just one way that an asymptote will present itself, depending on the behavior of the function. And we also have these other things called slant asymptotes, where you can get different lines. You can have that sort of line not just be horizontal or vertical. I'm not going to talk about that quite as much just because it's an extra layer of complexity, an extra layer of issue that doesn't come up quite as often, isn't quite as relevant to a lot of things that I am interested in for us to see, and also because we've done a lot this week already, I don't feel that we need to get that as well. Anyway, if we want to talk about vertical asymptotes in particular, what we need to do is identify the roots in the denominator of our rational function that are not roots in the numerator. So thinking back to our very first example, when we were talking about that x squared minus 9 over x minus 3 type of thing, having a 3 in the denominator made it 0, but that could also be simplified a little bit. That could be rewritten to be something very close to x plus 3. That could be back-ended to something a lot more manageable, where that type of problem doesn't actually indicate an asymptote exists. That's actually a thing called a removable discontinuity. That is a hole we can plug in the graph if we make an adjustment. And when we're talking about asymptotes, we're doing things called infinite discontinuities. That's a bit of language, you don't need to worry about that much right now, but it is worth mentioning in this context. Anyway, when we want to find a vertical asymptote, just to be sure, we are looking for a place where that doesn't happen. Something like 1 over x. You can't get rid of the root at 0 for x, because 0 never equals 1, you're just stuck with it, and that causes a vertical asymptote to appear as the function tries its best to figure out what it needs to do there. Really what ends up happening is that the 0 value in the bottom, as we approach that, that's going to end up becoming a very, very small number, and that very, very small number isn't canceled by anything in the top. So no matter what happens in the top, that's just going to be a value. Take a value over something very small, and you get something very large, either positive or negative, depending on the sign of what's going on in the denominator, and we'll see this here with a couple of examples. So for this, we want to find the vertical asymptotes, should they exist, of x over x squared minus 1 and x minus 1 over x squared plus 2. So in the first case, when we think about the denominator of that function, when we think about x over x squared minus 1, we can factor that denominator down there because it's a difference of squares into x minus 1 times x plus 1. And because neither of these factors is also a factor in the numerator, that indicates we will have vertical asymptotes at both x minus 1, x equals negative 1, excuse me, and x equals positive 1, which could be graphed like so. And that's how we'd be able to describe those locations. That's how we'd be able to recognize those locations. On the other hand, for x minus 1 over x squared plus 1, we can't really factor this. you can kind of hope to factor this into something like x minus 1 over x plus I times x minus I, but when we're talking about these things, remember, we're kind of avoiding cases for dealing with complex and imaginary things, so actually that's not really a concern for us. This, in terms of the real numbers, can't be factored into anything else, and because we can't factor it into anything else, we don't have to worry about whether or not the factors cancel. And so we don't actually have any vertical asymptotes. Our graph is just going to look something like this instead. Where what we can notice as well here, though, is that in our first case, as we let x approach negative infinity, it seems like it's going to be approaching 0. As we let x approach positive infinity, it also seems like it's going to be approaching 0. And the same sort of thing happens with this guy. But how can we tell for sure if those are horizontal asymptotes that we have there for y equals 0, that it's not going to cross the x-axis? Sorry if I misspoke there and said x a couple times where I shouldn't have. There's a lot of x's and y's here. It's easy to make that silly mistake. And that's what we're going to talk about next, though. Not making those mistakes, but how we can identify potential horizontal asymptotes on the other hand.